Let's take a quick review of linear transformations. Remember, transformations are just functions from one space to a next. There is a domain and a codomain, and a linear transformation, well, transformation in general, will just assign to each element of the domain an element in the codomain called the image of the element under the transformation. Linear transformations have particular requirements. Linear transformations have to respect scalar multiplication and vector addition, and most importantly, in linear transformations, a linear transformation is just matrix multiplication. I think when the question first came up, can we just say matrix multiplication is a linear transformation? I'm like, whoa, no. But that was not correct. That is the one time where we can separate things over. The reason that I immediately said no was that we don't want to say things like the matrix is consistent. We're starting to mix up our terminology with things that don't go together. But a linear transformation is just a matrix multiplication. So if we have a linear transformation, if T maps, let's say, Rn to Rm is a linear transformation, then there is an M by N matrix A such that T of X is A times X for all X in Rn. If you have a linear transformation, then there is a matrix that implements the map. So some of the problems phrase it this way. Find a matrix that implements the map. Oops, not the mat, the map. So if T maps Rn to Rm is a linear transformation, there is an M by N matrix A such that T of X is equal to A times X for all X in Rn. So in this case, Rn is the domain. That's where things are starting out. Here's the domain, Rn. The codomain is Rm. T is the map that goes from one space to the other, from the domain to the codomain. X is some vector in Rn, and the image of X is just A times X. So if T is a linear transformation, then there is definitely some M by N matrix A that will implement the map from Rn to Rm. Let's make sure that this makes sense. So if we look at the product AX, if we look at the product AX, A is M by N. A is M by N, and X is in Rn, so X is N by 1. So if A is M by N, then X has to be N by 1 for the multiplication to be defined. And then the result will be an M by 1 matrix, because AX will just be a linear combination of the columns of A. So AX is M by 1. So these two are equal, so this multiplication is defined. So it makes sense that T maps Rn to Rm, is implemented by an M by N matrix? Any questions? Cool. Let's look at an example. So in the if we have a matrix A, so let's say that T maps R2 to R3 is given by T of X equals AX, where A is this matrix. 1, -2, 3, -2, -1, 2. This was the example that was, oops, a little wonky. This is the example in Unit 3, where we talk about linear transformations. So first of all, let's make sure that this makes sense. If I want to multiply A times X, then X has to be 2 by 1. And that makes sense because the domain is R2. So X is something in R2. We multiply it by a 3 by 2 matrix, and the result will be a 3 by 1 matrix. And that makes sense because AX is a linear combination of the columns of A. The columns of A have 3 entries, so AX will also have 3 entries. So all these things are connected. T is R2 to R3. That tells us that A is going to be 3 by 2. Because we have to multiply by something from R2, so that means A has to have 2 columns. And it's going to end up in R3, so A has to have 3 rows. So those are the different ways that we can make sure that we know the domain, the codomain, and how those are related to the size of the matrix that implements the linear transformation. So the first couple of problems are just implement the map. So if U is 2, 0, and V is 3, -2, find T of U and T of V. So all that we want to do here is run these vectors through the transformation. So T of U is just going to be A times U. So it's just going to be this matrix, 1, -2, 3, 2, -2, -1, 2 times 2, 0. So that will just be 2 times 1, -2, 3, just doing matrix multiplication, plus 0 times -2, -1, 2. So that's just going to be 2, -4, 6. Find the image of U under T. We just use matrix multiplication, and we're thinking of matrix multiplication as making a linear combination of the columns of A using the entries in U as weights. So AU is a linear combination of the columns of A using the entries in U as weights. So just do matrix multiplication to find the image. Plug the vector into the function, find the image. And this would be the answer. Any questions? For T of V, to find T of V, we just do A times V. So we just take A, 1, negative 2, 3, negative 2, negative 1, 2, and multiply by the matrix, the vector, 3, negative 2. So that'll just be 3 times 1, negative 2, 3, minus 2 times negative 2, negative 1, 2. So we'll have 3 plus 4 is 7, and then negative 6 plus 2 is negative 4, and then 9 minus 4 is 5. So there is T of V. Oops, scroll. Now we're just finding a linear combination of the columns of A using the entries in V as weights. We could also think of this matrix multiplication by doing row column multiplication. So just dot products, 1 times 3 minus 2 times 2 times negative 2 is 7. Negative 2 times 3 plus negative 1 times negative 2 is negative 4. 3 times 3 plus 2 times negative 2 is 5. So we can also do row column multiplication. But that's mechanical. That's not sophisticated by thinking about linear combinations. There's a whole unit on linear combinations, so we should be thinking in terms of linear combinations. Any questions? Since we can, the thing that we do with equations, we can plug stuff into equations. I can give you the input and ask for the output. I can also give you an output and ask for an input. So I could say, let's suppose that B is negative 9, negative 2, 5. Let's suppose that B is negative 9, negative 2, 5. And I could say find X in R2 such that T of X equals B. I can give you an output and ask you to find the input. What X will lead to negative 9, negative 2, 5? This would be equivalent to saying solve AX equals B. And now this transformation business starts to look like stuff that we've done before. If we're here to solve a matrix equation, we'll use an augmented matrix to do so. So I'll go 1, negative 2, 3, negative 2, negative 1, 2, and I'll make an augmented matrix with negative 9, negative 2, 5. So now I'm looking at an augmented matrix. I need its reduced echelon form. I know the first 2 columns of the reduced echelon form are going to be 1, 0, 0 and 0, 1, 0. I know that I have pivots there. How did I know that I'm going to have, those are going to be the first 2 columns of the reduced echelon form? Take a minute and decide, how did I know that that was going to happen while I enter the matrix? Not the cool matrix. I'm just entering a matrix on a calculator. They're not multiples. It's only 2 columns. There's only 2 columns, and the second column is not a multiple of the first column, so these 2 columns are definitely linearly independent. That not multiples things only works when we're dealing with just 2 columns. Because now we're looking at 3 columns, and I can't say, well, negative 9, negative 2, 5 is not a multiple of these first 2 columns. And so therefore, these columns are linearly independent. That doesn't work with 3. The not multiples things doesn't work with more than 2 vectors. So it might be a combination of the first 2 vectors. So I put in 1, negative 2, I can't even see it in my original, there we go. 1, negative 2, negative 9, negative 2, negative 1, negative 2, 3, 2, 5. Find the reduced echelon form, and I got 1 by columns, 1, 0, 0, 0, 1, 0, negative 1, 4, 0. So we got a lot of information here. This augmented matrix does not have a pivot in the rightmost column. Therefore, this equation is consistent. The equation AX equals B is consistent. That's true, that's not what we're looking for. We can see that the solution, x1 is -1, x2 is 4. Tell me, what is x3? He said, setting an obvious trap in front of you, wondering if you are in fact superheroes and automatically have to step into the trap. x1 is -1, x2 is 4. What's x3 equal to? There is no x3. This is an augmented matrix. So there's an x1 and an x2. This is the augmented part of the augmented matrix. So we've got everything that we need here. So we see that x1 is equal to -1 and x2 is equal to 4. There is no x3. So the vector x that we were looking for is -1, 4. So one thing that was trickier than that was not intended to be tricky, but ended up being tricky, is that I asked for the parametric vector form of solutions where there was a unique solution. This is the parametric vector form of the solution set to this matrix equation. This is parametric vector form. There just happens to not be a parameter. This is parametric vector form. So the parametric vector form, there was just one. One thing that happened a lot in linear combination, in the quiz, linear combinations 2, was that you listed x3 when there was no x3. Notice that that T maps R2 to R3. Scroll up. T maps R2 to R3. So all the vectors x have to come from R2. I'm multiplying AX, and A has 2 columns, so X can only have 2 entries. There is no X3. There's a lot of ways that we can conclude that there is no X3. And we have that all that evidence is out there in front of us. We just have to train our mind to look for it. We have to train our eyes to see those things. Any questions? Great. So the point that we want to make here is that when we have a linear transformation, there is some matrix that implements the map. Also, a matrix multiplication is a linear transformation. So let's go on to another example. The other way you can be presented with linear transformations is just by a description of what's going on. So in the first example, we were given a matrix multiplication, and that was our linear transformation. So let's look at my next example. I think it's the same. Ooh, I'm so predictable. So let's So the other thing that we want to be able to do with linear transformations is to find the standard matrix of a linear transformation. We want to find the standard matrix of a linear transformation. Let's look at an example. This is a thing we want to do. Let's let T map R2 to R3 again, be given by, let's say, T of x1, x2. I have to start with something from R2, and I have to give you something in R3. So I'm going to make the first entry is x1 minus 2x2. The second entry is minus 2x1 minus x2. And the third entry is 3x1 plus x2. So instead of giving you the matrix that we know where we know it's a linear transformation, I'm just giving you this linear transformation and kind of telling you that it's a linear transformation. So we want to find the standard matrix of a linear transformation. We're looking at a linear transformation. We know that there's a matrix that implements this map. So to find the standard matrix of a linear transformation, what we want to do is map the basis vectors. To find the standard matrix of a transformation, we want to map the basis vectors. To find the standard matrix of a transformation, we want to map the basis vectors. To find the standard matrix of a linear transformation, we map the standard basis vectors. This did not plan out well. In practice, I fit this all on one line, so I was just able to write underneath it. So to find the matrix of a transformation, we map the standard basis vectors. So on Wednesday, if I'm like, oh, how do we find the matrix of a transformation? You're going to be like, I'll map the basis vectors. That's what we do. We map the basis vectors. The images of the basis vector, the basis vectors under the transformations, under the transformation, are the columns of the matrix of the transformation. The images of the basis vectors under the transformation are the columns of the matrix of the transformation. The images of the basis vectors under the transformation are the columns of the matrix of the transformation. If we want the standard matrix of the transformation, then we'll map the standard basis vectors. So if we insert in here standard, if we map the standard basis vectors under the transformation, we'll get the columns of the standard matrix of the transformation. So we haven't got to alternate bases for a vector space, but a basis for R2 is just two linearly independent vectors in R2. The vectors that we use as standard are 1, 0, and 0, 1, because it's easy to write everything in terms of 1, 0, 0, 1. But all we really need is two linearly independent vectors. So 1, negative 2 and 3, negative 2 is also a basis for R2. If I want the matrix of the transformation relative to that weirdo basis, then I map those weirdo basis vectors. I'm just kind of planning things for the future. Right now we have the standard matrix, and we get that by mapping the standard basis vectors. So I realize that I have not talked about standard basis vectors. So I'm just going to state that now. The standard basis for R2 a basis is a set of vectors, 1, 0, and 0, 1. A basis for a vector space is a linearly independent set of spanning vectors. A basis is just a linearly independent spanning set. A basis is a linearly independent spanning set. 1, 0, 0, 1 spans all of R2, and if I put those into a matrix, we'll see that that matrix would have a pivot in each column, and so the set of vectors is linearly independent. So what we want to do is map the basis vectors. That's the short form of what to remember. So I'm going to find t of 1, 0. So t of 1, 0. So x1 is equal to 1, x2 is equal to 0. That's what's going on here. x1 equals 1, and x2 equals 0. So according to this map, I do x1 minus 2x2. So I do 1 minus 2 times x2. Then the next entry is negative 2x1, negative 2x1 minus 1 times x2. And the third entry is 3x1 plus 1 x2. And so we get 1, negative 2, 3. That's the image of the first standard basis vector. This will be the first column of the standard matrix, because we're going to write it as a row, but it's going to show up as a column. This is the first column of the standard matrix. That's the first column of the standard matrix of the transformation. If I map the second basis vector, t of 0, 1, now x1 is equal to 0, and x2 is equal to 1. And we're starting to see why this is the standard basis. It's so easy to work with. So we're just going to do 0. X1 minus 2x2 is going to be 0 minus 2 times 1. The next entry is negative 2 times 0 minus 1 times 1. And then the next entry is 3 times 0 plus 1 times 1. This is in gory detail. You should absolutely not write this much detail, even if I say show your calculations. So the second column of the standard matrix will look like 0 minus 2, so negative 2, 0 minus 1, negative 1, and then 0 plus 1, 1. So the second column of the standard matrix of the transformation is negative 2, negative 1, 1. So the standard matrix of the transformation is going to be the first column is going to be 2 columns. First column will be 1, negative 2, 3, and the second column will be negative 2, negative 1, 1. Oh. Just ran out of paper. That's terrible timing. So the standard matrix of T first column was 1, -2, 3, and the second column was -2, -1, 1. Any questions? You absolutely can and should just eyeball the standard matrix by looking at what the transformation says. The first entry is just, so if we look at this, the image, so T of X is going to be, the first entry is x1 minus 2x2, and then -2x1 minus x2, and the third entry is 3x1 plus x2. And if I just break this up into its parametric vector form, I can see I get a 1, -2, 3 plus x2 times -2, -1, 1. And we can see that those are going to be the columns. We can easily see what the matrix is going to be just by looking at the transformation. You can and should do exactly that. If I give you this transformation, if I say find the standard matrix of this transformation, the next and only thing that you should write is this matrix here. But that's how we find the thing. That is not how we're going to be thinking about the thing. We think about the thing by saying the standard matrix of the transformation will be the images of the standard basis vectors. To find the standard matrix of a transformation, you map the basis vectors. Any questions? So, perfect question. Can't you just eyeball this? Yeah, and you should eyeball it. But that's not how we're going to think about it. We're going to think about mapping the basis vectors, because that's going to reinforce our notion that the transformation is linear and that the transformation, a linear transformation respects linear combinations. Those are the important things that go along with it. Plus, it's not going to be easy to eyeball if I ask for the transformation relative to some weirdo basis, wherein we map the basis vectors. Any questions? Well, we haven't talked about weirdo bases yet, so. Technical term, weirdo base. Kidding, we don't call them weirdo bases. Only I call them weirdo bases. If you go on to your next math class and you start talking about weirdo bases like it's a thing, people are going to think that you're strange. They're going to think, in fact, you are a weirdo. All right. And I'm not famous enough that people to be like, oh, weirdo bases, you must have come from Leach's class. Because I'm like not famous. I'm like stupidly famous. Like I'll go into a restaurant in my local area and then like one of the waiters will be like a student and they'll be like, oh, Professor Leach. I'm like, oh, hey, student of mine from a while ago. And then they'll be like, oh, dude, I'm in your class right now. I was like, well, yeah, yes, of course. But I haven't seen you since a while ago, like this morning when you were in my class. I wasn't there. It's like, oh, yeah, yes, I noticed. And then they'll be like, oh, can I get you anything? I'm like, oh, just water for now. And then I get up and leave because I'm like, oh, dude, I can't have one of my students be my waiter. I don't know if I flunked them. What if they have an axe to grind with me? So I just go, I got to go to restaurants that are not in my local area. I'm just kidding. Sometimes I know that you're flunking me and I'm flunking you and I definitely leave. I'm just kidding. I give you extra credit if you bring me an extra order of fries. I'm just kidding. All right, let's pause the video and then we'll start taking questions from 1.8 and 1.9. So next video ends here. Let's pause the video.